Today we're going to be talking about one of the most simple but also efficient algorithms from the world of computer science, binary search. It's really a fundamental building block of more sophisticated algorithms. Welcome to Kopec Explains Software, the podcast where we make computing intelligible. Today we're going to be talking about binary search, a fundamental algorithm in the world of computer science.
What's binary search used for?
Binary search is a simple algorithm for taking a sorted data set and finding a particular item within that sorted data set.
Is there an alternative?
Another algorithm is known as linear search. Linear search does not depend on the data set being sorted, so linear search can work with any data set, whereas binary search requires that the data set be sorted.
So what prerequisites does a data set need to have to be used for binary search?
The data type that the data set is composed of must be orderable. What do I mean by orderable? I mean that I should be able to take two different items from the data set, so two different items that are of the same data type because the data set is composed all of items of the same data type, and I should be able to compare the two and tell something about which one should come first in a particular ordering. Let me give you an example. If I have two integers, I have the numbers 10 and 25. I can tell you that if I want to put them in ascending order, the number 10 will come before the number 25. Or let's say I have letters. Let's say I have the letters L and Z. I can tell you that if I want to put those two letters in ascending order, the letter L will come before the letter Z. So whatever the data type that the data set is going to be composed of must be orderable. I must be able to put any of the data items in order.
Can a software developer make any data type orderable?
Yes, some data types have an intrinsic natural ordering to them. For example, we talked about integers before. Of course, they have a natural numeric order to them. And when we talked about letters before, they have a natural alphabetic ordering to them. And so they have an intrinsic order that is fundamental to how they're typically defined in a programming language. In this case, that being the data types integers or strings, or characters perhaps. Other data types, custom data types that a programmer defines, like let's say I define a data type for a car. Well, how do I order two cars? How do I decide which car comes first? As the programmer, that's going to be up to me. I'm going to get to determine how that custom data type is ordered. How do I decide if a Ford comes first or a Honda comes first? Maybe it has to do with the year that the car was manufactured. Maybe it has to do with the first letter of the manufacturer's name. Maybe it has to do with a combination of multiple factors. Yes, the programmer can define an ordering for any custom data type. And once they have, in order to do binary search, they need to actually go and take their data set of that data type and sort it.
So there's a good amount of work before you institute the algorithm.
Yes, you have to actually sort the data set before you run binary search. And sorting is actually quite expensive.
What do you mean by expensive?
In the lingo of computer science, sorting a data set of comparable types is a big O of n log n operation. Now, that's probably Greek to a lot of our listeners. Let me put it this way. It takes more time to sort a data set than it does to do either a binary search or a linear search.
So expensive in terms of time and energy.
Yes, absolutely. And it's going to be more expensive the more unsorted that the data set is, depending on what sorting algorithm you're using. But of course, if the data set is already sorted, that's a huge win. But if the data set is not sorted and we don't know how sorted it is or not sorted it is, it might just be in any particular order before we start, then it's going to be quite expensive perhaps to actually do the sorting. And the bigger the data set is, the more expensive it is to do the sorting.
All right, Dave, why don't you walk us through the algorithm?
Yeah, we did a lot of build-up, and actually a lot of the sorting algorithms are quite complicated, and sorting itself would be beyond the scope of this episode. So now we're going to get to the real actual meat of this, the binary search algorithm itself. So in binary search, it's best to learn it with an example. So let's say we take the numbers 0 through 100, and we have a data set composed of the integers 0 through 100. And you're thinking of a number, and I don't want you to tell me right now what that number is, okay?
Okay.
And we're just going to walk through it. So I'm going to take my first guess. My first guess is that your number is 50.
No.
Is your number less than 50 or greater than 50?
Less than.
Okay, is your number 25?
No.
Is your number greater than 25 or less than 25?
Less than.
Is your number 13?
No.
Is your number greater than 13 or less than 13?
Greater.
Okay. Is your number 19?
No.
Is your number less than 19 or greater than 19?
Less.
Okay. Is your number 16?
No.
Is your number greater than 16 or less than 16?
Less.
Okay. Is your number 15?
Yes.
Okay, wow, I found your number. So how many guesses was that for me to find your number?
I think it might have been 7.
Okay. I think it was less than that, maybe. Let's count. So I first did 50, then I did 25, then I did 13. We're up to 3 guesses. Then I did 19, that's 4 guesses. Then I did 16, that's 5 guesses. And then I did 15, that's 6 guesses.
Okay, sorry. 6
So
guesses.
yeah, 6 guesses, right? And your number was 15. Now let's say I just asked you all of the numbers in order starting at 0. So I would have said 0, then 1, then 2. How many guesses would it have taken me to get to your number 15?
16.
Right, it would have taken me 16 guesses. So obviously 6 guesses is less guesses than 16.
Sure.
Yeah, it's much more efficient. What I was just doing there was a binary search. In a binary search, it's very simple. Because you know the data set is sorted, you just keep dividing the data set in half. So when I made the first guess of 50 and you told me the number is less than 50, I have just excluded half of all the numbers. We no longer need to search through them. So the numbers 51 through 100 I've just totally excluded. And I know that your number's not in that range, so I'll never need to touch them again. Then when you said your number was less than 25, I'm able to exclude all of the numbers between 26 and 50. Then when you said your number is greater than 13, I'm able to exclude all the numbers between 0 and 13. So every time that I made a new guess, I was excluding half of the remaining data set. It turns out that if you keep doing that, you're going to end up being able to find the ultimate number in log base 2 of the number of items in the data set. So in this case, there were 100 items in the data set. Log base 2 of 100 is approximately 7. It's actually a little bit less than 7, but it's approximately 7. That means that it will take me no more than 7 guesses to find any number between 0 and 100 using this method.
Regardless of the size of the data set.
No, the data set, if it has exactly 100 items,
Oh, I see.
then it will be log base 2 of 100. If the data set had 1,000 items, then it would be log base 2 of 1,000.
I see. Okay.
What's log base 2 of 1,000?
Is it like 12?
It's about 10. That's amazing. That means that if I have 1,000 items in just 10 guesses, I can figure out what the item is. And because it's a log scale, it's incredible that I can do so few guesses for even millions or billions of items. For example, if I have 1 billion items using this method, because 2 to the 30th is just a little bit more than 1 billion, it would take me only 30 guesses, maximum, to find any item in a data set of 1 billion that's sorted.
That's a pretty powerful algorithm.
Right, now think about if I had 1 billion items and I was doing another search method called linear search. Here's how linear search works. With linear search, I just start at the beginning and I keep asking, is this the item I'm looking for? Is this the item I'm looking for? So we talked about this earlier. If your number was 15 and I was looking for the number 15 in a data set of the numbers 0 through 100, I would first ask, is your item 0? Is your item 1? Is your item 2? Etc., right? So I'd get to number 15. Now, imagine that you had 1 billion items and I was looking for any arbitrary number. It doesn't even matter. Let's say I was looking for the 300 millionth item in the data set of 1 billion. If I'm doing binary search, I know it'll take me no more than 30 tries to find that item. If I'm doing linear search, it will take me 300 million tries to find that same item. So this simple idea of just having the data set sorted and dividing it in half every time to eliminate a huge number of items by just comparing the item that's in the middle to the item that I'm searching for will allow me to reduce my search time many orders of magnitude.
So it's worth it to put all the effort into sorting.
Maybe. And let's come back to that in a minute. But before we do, I'd like to just walk through a little more formal definition of the algorithm. So let's go back to just a simple example where we have the numbers 0 through 100. So the first thing we're going to do is make sure that the data set is sorted. So we make sure those numbers 0 through 100 are in order. And in this case, we're talking about ascending order. And what we do is we start in the middle. So we find the middle element. And then once we found the middle element, we check, is the item that we're looking for less than that middle element or greater than that middle element? And whatever half it's in, we now make that the new area of our search space. So we might be now moving the upper limit or the lower limit of all of the items we're searching for. So for example, after we found out it's not 50, we're either now going to make 50 the lower limit and keep the upper limit at 100. So we're looking at the numbers 50 through 100, or we're making 50 our upper limit and we're making our lower limit 0 still, and we're looking at the numbers 0 up to 50. So we're going to do this and then we're just going to do it again. So whatever we now made our new search range, we're going to find the middle element and again, reduce the search space by moving the upper limit or the lower limit to now reduce that search space to half of what it just was. And we just keep doing that over and over and over again until we've gotten to the actual item. In computer science terms, this means that it's a big O of log of n to find any item in the worst case. And we're actually going to need to use just a constant amount of space because we just have one item at a time that we're looking at and comparing to. So there's just whatever space the original data set took up and really basically no additional space needed, just a little bit of additional space needed to do the comparisons. So it's an incredibly efficient algorithm, really, really powerful algorithm that's at the core of a lot of searching, and then is also a building block for a lot of data structures and algorithms that are more sophisticated than it.
So it sounds like binary search is more practical than a linear search.
Well, earlier I told you it depends. Here's the thing. If the data set is not sorted, I mentioned earlier it's very expensive to do the sorting potentially. And that might mean it's actually not worth it. So it actually is going to take more time on average for most unsorted data sets to do the sorting than it would to do a linear search. So let's say, again, I have that big data set of 1 billion items, okay? And let's say it's not sorted, okay? And remember, I said I need to look through 300 million items maybe to find the 300 millionth item using a linear search, right? And in the worst case, if it's not sorted, I might actually have to look through all billion items, because what if what would be the 300 millionth item, if it was sorted, actually happens to be the billionth item when it's not sorted? So doing a linear search, it might actually take me looking through every single item to find or not find the one that I'm looking for. On the other hand, it turns out that sorting 1 billion items that are unsorted will actually be more expensive than looking through 1 billion items. And so, if I only need to do this search one time, and it's not sorted, it actually might make sense to use linear search. Even though binary search is so much more efficient than linear search, doing the sorting is so expensive that it still might make sense to use linear search. And so you're actually going to need to do an analysis and think about, is the data set sorted? If it's sorted, it always makes sense to do binary search. However, if it's not sorted, then you need to analyze how expensive will it be to sort it and how many searches do you want to do. If you're only going to ever do one search, it makes sense to just do a linear search and not bother with the sorting. And actually, there's a certain number of searches, and this is again going to depend on the exact constant factors involved and the size of the data set and what sorting algorithm you're using to actually sort it. But you'll have to do all of that analysis. There's a certain number of searches that you're going to do when it actually makes sense to go ahead and do the sorting and then do a binary search versus just doing a bunch of linear searches. So the answer, unfortunately, is I can't just tell you fundamentally this is the better way to go. It depends on the situation. But if it's already sorted, it always makes sense to do a binary search. Let me give you 2 just example scenarios that kind of illustrate this. Let's say you're looking in a dictionary. A dictionary is always sorted, right? The words are always in alphabetical order. So it always makes sense to do a binary search when looking for a word in a dictionary, not to do a linear search. Now imagine you're at a train station and you're in a lobby and you find somebody's ticket, okay? And let's say there's about 50 people in that train station lobby and that ticket was on the ground, right? You have two options here. You could ask all the people to get up and put themselves in alphabetical order. So ask them to talk to each other, and you're going to use some sorting algorithm. Maybe you're going to be the conductor here and arrange everybody in order, right? Or you could you'd have to do that to sort them so you could then do a binary search on them, right? Or you could just go ask each person individually. That's a linear search, right? Are you the person who dropped this ticket? Are you the person who dropped this ticket? Maybe you have to ask them to show some ID so they're not stealing the ticket. But that would be much more efficient, obviously, right? And that's a one-time thing. You're never going to find that ticket again that same day on the ground again and have to go through all the people again. So it doesn't make sense to go through the expense of sorting them so that you can do the more efficient binary search algorithm. So the answer is which one you're going to use really depends. But if the data set is already sorted, you're always going to use binary search because it's eons more efficient than linear search on average.
Is binary search easy to implement for a programmer?
Absolutely. Binary search is very easy to implement. It's just a handful of lines of code. Linear search is even easier. It's only like 2 or 3 lines of code in most programming languages. But yeah, there's really no impediment to implementing binary search. It's incredibly simple to codify the algorithm that we talked about earlier.
Well, binary search seems like a pretty powerful algorithm and a pretty useful one too.
Yeah, and it's incredible how simple it is and how much more efficient it is than linear search. But it has that big caveat: the data set must be sorted before we use it, whereas linear search works on any data set. All right, thanks for listening to us this week. Rebecca, how can people get in touch with us on Twitter?
We're at Kopec Explains, KOPECEXPLAINS.
Thanks for listening, and we'll see you in 2 weeks.
Bye.